The solution of the differential equation d z is a function of x and y plus x into z is a function of xy into dx plus y into z is a function of xy into dy is equal to 0 is. Here the differential equation that we have given as dz, of course this z is a function of x and y, then we can write it as x comma y plus x into z which is a function of x and y into dx plus y into z which is a function of x and y into dy is equal to 0. Now dividing this equation by dividing this by z which is a function of x and y, then we can write it as this dz by z, and of course this z is a function of x and y, and plus x into dx plus y into dy is equal to 0. Now on integrating we can write it as this ln of z plus x square by 2 plus y square by 2 plus say the ln of c is equal to 0. Now combining these two logarithmic terms, we can write it as ln of z into c is equal to minus x square plus y square divided by 2. Taking the exponential on the both sides, then we can write it as z into c is equal to e to the power minus x square plus y square divided by 2, and from here we can write it as z is equal to 1 by c into e to the power minus x square plus y square divided by 2, and 1 by c is replaced by some another arbitrary constant, then z is equal to some capital C is into e to the power minus x square plus y square divided by 2, and hence the solution of the differential equation is represented by this equation. Consider the differential equation dy by dx is equal to y square by x with the boundary condition y at x is equal to 1 is 1. Out of the following, the range of the x in which y is the real and the finite is. Here the differential equation we have to given is dy by dx is equal to y square by x. Now on the observation we can solve this differential equation using variable separation technique. Therefore we can write it as dy by y square is equal to dx by x. Now on integrating both sides we can write it as minus 1 by y is equal to ln of x plus some arbitrary constant c. Now using the initial boundary condition given here that at x is equal to 1, then y is equal to 1, then this left hand side term become minus 1, and this is ln of 1 plus c, and this term is 0, therefore c is equal to minus 1, and substituting this value of c in this equation we obtain final solution as 1 by y is equal to ln of x minus 1. Now from here we obtain the value of y as this y is equal to 1 divided by 1 minus ln of x. Now on the first looking here, this if this x is equal to some value of e, because this ln is the natural logarithm and we know that this the natural logarithm at e become 1, therefore 1 minus 1 is 0, and this whole term is tending to infinity. That means this x is equal to e, this y is tending to infinity, and what is the value of e? Value of that is 2.732 something like. Now from here if we put this x is equal to 0, then this function, this ln of 0 become minus infinity, and this denominator term become 1 minus into minus infinity means 1 by infinity. That means y is equal to 0, where at x is equal to 0. That means what I am saying, that if x is equal to 0, that means this y becomes 0. Now, and what is the behavior of this function between the 0 to this value of e? From 0 to this e, this is this function that is y is increasing and increasing up to the infinity. At the value of e, it become infinite. And what after the e? Value of e. Then after the value of e, this function is again start from the negative. Suppose we take the value of something more than this e, then this function is gradually increasing and tending to 0 if we take this x to the infinite. And what happened if we take the x is equal to 3 and to infinity, mean in the positive range? Then in the positive range, this function is finite, because this is infinite at only e, and e means 2.732, this particular value. And what is the behavior of 3 to infinity? 3 to infinity, this is function, this is e, and somehow here this is our point is 3, and this 3 to this infinite, this function y have some finite value, and of course this is tending to 0 if we move in this direction, x direction, to infinity. And hence the behavior of y is real only for the window of x. X means this is starting from the 3 to the infinity. And what is the behavior at 3? The behavior at 3 is also it is the finite value, because it is infinite just less than 3. The value of less than means this particular value of e, x is equal to e, and hence which is correspond to the option D, and hence option D is the correct option. Consider the two particles moving along the x-axis in terms of their coordinate x1 and x2. Their velocities are given as dx1 by dt is equal to x2 minus x1 and dx2 by dt is equal to x1 minus x2 for the second particle. When they start moving from the initial location of x1 at t is equal to 0 is 1 and x2 at t is equal to 0 at minus 1, the time dependence of both x1 and x2 contain a term of the form e to the power at, where a is a constant. Then the value of a is we have to find. Now here the path for the both the particle is given here. Like for the first particle is dx1 by dt is equal to x2 minus x1. Say this is the equation number 1. And for the second particle, dx2 by dt is equal to x1 minus x2. Now, on observing this equation 1 and equation 2, then we can write it as this dx1 by dt is equal to minus k dx2 by dt, and on integrating this, we can write it as x1 is equal to minus x2 plus c, and of course this x1 and x2 are the function of time. Now applying the boundary condition that x1 at t is equal to 0 and x2 at t is equal to 0 are 1 and minus 1 respectively. This is 1 and this x2 is minus 1 at t is equal to 0. And from here we obtain that this arbitrary constant c is equal to 0, and hence from here finally we can write it as x1 is equal to minus x2. This is equation number 3. Now using this equation 3 for the path of the first particle, which is given by the differential equation that dx1 by dt, and this first equation is reduced only in terms of the x1 using this equation 3. Therefore we can write here in the place of x2 we can write it as this x minus x1 minus x1, which is become as minus 2 times of x1. Now we can to solve this differential equation, we use the variable separation technique, and by using this technique we can write it as this dx1 by x1 is equal to minus 2 times dt, and on integrating we obtain this as ln x1 is equal to minus 2 times t plus some integrating constant, say c1. Now this integrating constant adding in term of the ln c1, because here one term in the logarithmic scale, therefore we add it in term of logarithmic, and hence this can be written as this ln x1 by c1 is equal to minus 2 times t. Taking exponential on both sides, we got this x1 by c1 is equal to exponential of minus 2 times t, and of course this c1 is multiplied on this right hand side. Now using the initial condition that x1 at 0 is 1, then we can write it as 1 at t is equal to 0, then this c1 and into this exponential term become 1, and hence from here we obtain that this c1 is equal to 1, and the solution for the first particle is written as this e to the power minus 2t. This is our path of the first particle. Now for the path of the second particle, we write the second equation that dx2 by dt is equal to minus x2 minus x2, because we have substituted in this equation 2, this x1 is replaced by this minus x2, and we got the differential equation only in term of the x2, which can be further write it as minus 2 times x2. And now using the variable separation technique as the first particle, we can write it as dx2 by x2 is equal to minus 2 times dt, and on integrating we can write it as this x2 of logarithmic natural is equal to minus 2t plus some another integrating constant, say this c2, and after solving as in the first particle we can write it as x2 is equal to c2 into e to the power minus 2t. Now applying the initial condition for the x2 particle at t is equal to 0, this x2 become minus 1, therefore we write it as minus 1 is equal to c2 into this exponential term become 1, and from here we obtain c2 is equal to minus 1, and final solution is become as x2 is equal to minus e to the power minus 2t. Now this is the path for the second particle. Now both the solution of x1 and x2 comes in the exponential form. Of course this x2 is going in the negative direction with time, and here the value of a is an integer, which is on comparing this equation we obtain this a is equal to minus 2 from here, and hence this a is equal to minus 2. Which one of the following correctly represents symmetrically the solution of the equation df by dx plus 2f is equal to 3, such that f at x is equal to 0 is 0. Here the differential equation given us is df by dx plus 2f is equal to 3, and on observing this differential equation we can solve this using the variable separation technique, because this can be easily separate out variably. Like this can be written as this df divided by 3 minus 2 times f is equal to dx, and on integrating both sides we can write it as minus 1 by 2 into ln of this 3 minus 2f is equal to x plus some arbitrary constant in term of logarithmic, that is ln of c. Now combining the both term ln, we can write it as this this can be written as this ln of this 3 minus 2 times f to the power minus 1 by 2 minus ln of c is equal to x, and from here we can write it as ln of this 3 minus 2 times f to the power minus 1 by 2 divided by c is equal to x. Now taking the exponential on the both side, then we can write it as this 3 minus 2 times f to the power minus 1 by 2 divided by this arbitrary constant c is equal to e to the power x. Now substituting the initial condition, initial boundary condition, that at x is equal to 0, this f becomes 0. Therefore we can write here as this 3 to the power minus 1 by 2 divided by c is equal to exponential of this x is equal to 0 become 1, and from here we obtain that c is equal to 1 by square root of 3. Now again substituting the value of c in this above equation, we can write it as 3 minus 2 times of f to the power minus 1 by 2 divided by this 1 by square root of 3, which is become as this square root of 3 here, which is equal to the e to the power x. Now we have to separate out this f value in term of the x value. Therefore we raising the power on the both side by the minus 2, then this first term become as this square root of 3 to the power minus 2, and the next term is 3 minus 2f to the power minus 1 by 2 into the power minus 2 is equal to e to the power minus 2x. And here this 2 is cancelled out with this 2 and this minus with this minus, and from here we can write it as, and of course this term is square root is also cancelling with this 2, and only power minus 1 is becoming here. Then we can write it as 3 minus 2 times of f divided by this 3 become in the denominator and is equal to e to the power minus 2x. Now to solve this value of f, we can write it as 1 minus 2 by 3 times of f is equal to e to the power minus 2x, and for the value of f we obtain here f is equal to 3 by 2 into 1 minus e to the power 2x. Now if we substitute x is equal to 0, then our function f is become as this 0, because if we put x is equal to 0 here, then 1 minus 1 becomes 0 and f is 0. Now again putting the second condition that x is equal to as x tending to infinity, very large value, then this f can be seen from this expression that 3 by 2 into 1 minus e to the power infinity with the minus sign, and this term become as 0. Therefore this f value is tending to the 3 by 2. And for both of these conditions, there are the two possibility of the graphs, this b option and d option, but our function is the exponential only, and the exponential function, we know that the behavior of the exponential function can be easily understanding by this curve, that this starting from the 0, and the exponential curve is function is increasing slightly, and then it is saturate to the value here this function is saturated to the value with the 3 by 2 as this x is tending to infinity, and hence option B is the correct option here. If a function yx is described by the initial value problem d2y by dx square plus 5 times dy by dx plus 6 times y is equal to 0 with the initial condition y at x is equal to 0 is 2 and y dash at x is equal to 0 is 0, then the value of y at x is equal to 1 is what will be up to the 2 decimal places. Here the differential equation is given to us is d2y by dx square plus 5 times dy by dx plus 6 times y is equal to 0. Now this differential equation can be written in the operator terms by substituting dy by dx is equal to operator d and d2y by dx square is d square. Then this equation can be written as this d square plus 5 times d plus 6 into y is equal to 0. Now by substituting d is equal to m, we can write the auxiliary equation as m square plus 5 times m plus 6 is equal to 0. And from here, the root of this auxiliary equation can be easily obtained as m is equal to minus 2 and minus 3. Then the solution of this differential equation can be written as the root of this auxiliary equation are the real and the different. Therefore, the solution is written as c1 into e to the power minus 2x plus c2 into e to the power minus 3x. Now, using the initial condition, say this equation is A. Now, using the initial condition that at x is equal to 0, this y is equal to 2, then we can write it as 2 is equal to c1, as this exponential term become 1, and plus c2, this exponential term again become 1, and this is equation, say the B. Now, taking the derivative of this A, we can write as y dash of which is a function of x is equal to minus 2 times c1 into e to the power minus 2x minus 3 times c2 into e to the power minus 3x. On substituting the x is equal to 0 in this expression say the c, we can write as this y dash become 0 at x is equal to 0. This can be written as minus 2 times c1 minus 3 times of c2. This is expression say D. Now solving expression B and D, we can obtain the value of the arbitrary constant c1 and c2 as this c1 is equal to 6 and this c2 is equal to minus 4. Then the exact solution of the differential equation can be written as y is equal to 6 times e to the power minus 2x plus minus 4 times e to the power minus 3x. This is our final solution, is represented by the equation number 1. Now we have to calculate the value of y at x is equal to 1. Now on substituting this solution x is equal to 1, we obtain this 6 divided by this e to the power minus 2 into 1 means this e square with minus 2 power with minus 2 which is become as the 6 by e square, and the next term is minus 4 by this become as e to the power 3. Now e to the power 3 is approximated as 20 and e to the power 2 is 2.72 to the power 2, and this whole value is approximated as 0.6128, and for the two decimal places, or we can write it as 0.61, and hence the value of y at x is equal to 1 for the two decimal point is 0.61. The solution yx of the differential equation y into dy by dx plus 3x is equal to 0 such that y at 1 is equal to 0 is described by which of the following path. Here the given differential equation is here like y into dy by dx plus 3x is equal to 0. Now to solve this differential equation, we apply variable separation method because this equation can be easily solved by the variable separation techniques, and using the variable separation technique we can write it as y into dy is equal to minus 3x into dx. Now integrating on both sides we can write it as y square by 2 is equal to minus 3 into x square by 2 plus a arbitrary constant c. Now applying the given boundary condition, that boundary condition is given as y at x is equal to 1 is equal to 0. Now substituting y is equal to 0 with substituting x is equal to 1 in this above equation, say A. Here we can write it as 0 is equal to minus 3 by 2 into 1 square plus c, and from this equation we obtain that c is equal to 3 by 2. Now the final solution of this differential equation is written as y square by 2 is equal to minus 3 by 2 into x square plus 3 by 2. Now dividing by 3 by 2 on the both side, then we can write it as this y square divided by 3 is equal to minus x square plus 1. Now rearranging this term, we can write it as this x square plus y square by square root of 3 to the whole square, and of course we can write it as here 1 and its square is equal to 1. This is the equation for the ellipse whose the major axis along the y-axis with the value under root 10, which is calculated at 1.732, and the minor axis along the x-axis with the dimension of 1 unit. And we can plot this ellipse like that. This is our y-axis and this is our x-axis. Then this ellipse can be plotted as like this, with center at origin, and hence the option A is correct for this given question. Consider the second order ordinary differential equation such that y double dash plus 4 times y dash plus 5 times y is equal to 0 if y at x is equal to 0 is 0 and y dash at x is equal to 0 is 1. Then find the value of y at pi by 2 up to 3 decimal places. Here the differential equation is given as y double dash plus 4 times y dash plus 5 times y is equal to 0. This differential equation can be written in the term of d operator, and d operator is obtained as y dash is equal to d and y double dash is equal to d square. Then this differential equation is written as d square plus 4 times d plus 5 into y is equal to 0. And from this differential equation in differential operator term, we obtain the auxiliary equation, as this auxiliary equation is obtained by substituting d is equal to m. Then this auxiliary equation we obtain m square plus 4m plus 5 is equal to 0. Now from here we obtain the root of this auxiliary equation as this minus 4 plus minus 4 square means 16 minus 4 into 5 means 20 divided by 2, which gives us this minus 2 plus minus iota. And from here we notice that the root of this auxiliary equation are complex. Therefore the solution of this differential equation is written as y is a function of x is equal to e to the power minus 2x into some arbitrary constant a into sin x plus some another arbitrary constant b into cos of x. This is equation number 1. Now applying the boundary condition, first given that this y at x is equal to 0 is 0, then on applying in the above equation 1, we can write it as 0 is equal to e to the power 2 into 0. Then we can write it as 1 into a into sine at 0 is 0 plus b into cos 0 is 1. Therefore from here we obtain b is equal to 0. Now Now, by substituting the value of b in this obtained solution, we can again write the solution as y is a function of x is equal to e to the power minus 2x into a into sine of x. Now, taking the differentiation of this solution, y dash x is obtained as this a into cos of x into the derivative of this function is same as it is, and plus the derivative of this e to the power 2x we obtain, plus the derivative of this e to the power 2x is minus 2 times e to the power 2x into the sin x as it is. Now substituting the this second condition, that y dash at 0 is 1, then this y dash become 1 at x is equal to 0. This can be written as a into cos 0 become 1, and this exponential term also become 1 at substituting x is equal to 0. Now the second term 2 times e to the power minus 2x, this term become 1 and the sin x become 0, therefore this second term become whole as a 0, and from here we obtain a is equal to 1. Then the final solution, using the value of the arbitrary constant a and b, we can write it as y as a function of x is equal to e to the power minus 2x, and the value of a is 1, therefore this is become as sin x. This is our final solution. Now we have to find the value y at x is equal to pi by 2. Now substituting this x is equal to pi by 2, then we can write it as 2 times pi by 2 into sine pi by 2, and sine pi by 2 is 1, therefore this can be written as e to the power minus pi. Now using the scientific calculator, we got the value of 0.0415, which is approximated as 0.042 up to 3 decimal places, and hence the value of this y at pi by 2 is 0.042.